how does the digital transformation transforms the industrial sensor design? The industry is demanding more data, and more data is needed for improving the efficiencies uh, and improving the manufacturing of any factory, being it factories or process industry. Everybody's looking for more data and use the data for optimization of the process. So not only for control, but bringing the data up to a higher level of not only control, but enterprise and up to the cloud and process the data and find out how to make the factory more efficient. So what we talked about today is look at the instrument which is sitting at the edge of any process or factory system, and how does the transformation, looking for more digital and more data, how does it transform the design of the device itself? So we look at some connectivity types, architectures of 4 to 20 milliamp hour, and then APL, 10 base T1L, and then we deep dive into the field device design, look at power, explosive safety, functional safety, security, and hopefully we'll be able to draw some conclusions. So typical installations in the field. So on the left-hand side, it's a typical plant wire 4 to 20 milliamps. These plants are running for years, decades, 50 years. We have connected it from the end device. And by principle, it's very simple. There is a pair of wires going from the end device, from the edge, and it finds all its ways to the PLC input. And similarly, if you need to control some valve, it finds its way from the output of PLC, programmable logic controller, and control some valve. So principle very simple. The challenge comes with a scale. Even if I look at my own plant, we have a manufacturing facility in Analog Devices, and if I look at our own fab, there is hundreds and thousands of these nodes. They go through some field junction boxes. There is a piece of equipment somewhere, so the wires and cables from individual devices is congregated into some junction box, and then it goes through some multi-pair, multi-core shielded cable, and the cables are quite thick, lots and lots of wires inside, land up in marshalling cabinet. And just to paint the picture, the marshalling cabinets in our factory are like huge cabinets, and there are thousands of cables landing there. And then if you need to maintain it, if you need to add a node somewhere on some edge, and need to find a new wire there, the challenge comes with a scale, and maintaining such a plot is not an easy way. So by electrically, very simple, with the scale of the manufacturing, it's not that simple anymore. If you look at the right-hand side, that's what APL is looking for, having an Ethernet connectivity down to the sensors. Up until recently, that was not possible to bring Ethernet to these edges of many of the industries, because it could be sitting in an explosive environment, so it needs to be safe, explosive safe, intrinsic safe. But the new 10 base T1L Ethernet, or as the process industry calls it, APL, allows us to bring Ethernet down to the edge, and then it simplifies significantly the topology of the wiring. You have the same signals coming individually from the sensor, but they now come to a field switch, through what they call spores, up to 200 meters per APL specification, and then you can chain the field switches and get the information up to the what they call power switch for injecting the power to power supply all the sensors, and to the PLC. And what that brings it, you have an IP address on each of the sensor, and not only you can run the control signals between the control information between the sensor actuator and the programmable controller, you can in parallel on the same wires get much more data up the stream and process the data, and again use them for improving the efficiency and sustainability of the manufacturing. So now let's dive deeper here. So this is 4 to 20 milliamp. Again, sensor, PLC input-output, analog input-output. And reminder, it's analog signal. So it's 4 milliamps is 0% of temperature, zero pressure. 20 milliamps is the maximum, 100% of the input. And any value in between represents a value that is measured. That's 4 to 20 milliamps. Sometimes on the 4 to 20 milliamp, there is optional hard modulation, which does bring some digital bidirectional modulation, bidirectional information from and out of the sensor. Hard is pretty slow, 1.2 kilobit, which is slower than any modem that we saw 20 years ago on our telephone line, so it's really slow. And not every PLC DCS device would have a native hard modem on the port, so you may have a hard multiplexer aside that, again, complicates the wiring. If you look at the APL, again, the signal chain can have some 100 gigabit connectivity from the switch to the PLC, field switch or multiple field switches, and the spurs to the sensors and actuators. And the signal is digital. 10BASE-T1L is a PAM3, 3 levels modulation, digital, and you have DC power over the same line. So it's pure digital communication, no 4 to 20 milliamp and anything between. Now, architecture of the field instrument itself, and I focus in the presentation on the sensor side. Equal will be applying to any actuators, any valves, and devices like that. So typically a sensor measuring temperature, pressure, flow, distance, whatever needs to be measured there. Some analog front end, microcontroller, maybe two. You can see that it is relatively small on today's scale, small microcontroller, and communication. So the 4 to 20 milliamp communication would like that. You have a D2A converter, kind of taking the data, saying, okay, 0 or 100% convert to the current, and driving the current in the loop. And then, of course, you have some DC-DC step-down converter to supply the insides, the guts of the sensor. When you look at the field device on APL, the front end is very similar. You may need a little bit bigger microcontroller because you need to run some communication protocol on it. But then you have a PHY or integrated MAC and PHY, same DC-DC converter, and it's a digital communication there. And then power coupling, there are some power coupling inductors that couple decouple the power and data. So data is AC coupled to the communication, and power is DC coupled through an inductor. So, but the front end can look very similar to what we see today at 4 to 20 milliamps. Now we look at the power aspects of the instrument. 4 to 20 milliamp is the information. The system has to be able to power the full power needed for the device. So if it's signaling 20 milliamps, which is 100%, it needs to be able to deliver 20 milliamps at 24 volts to the system. And most of that 20 milliamps would then be burned or bypass or shunt through the communication stage of the device. And then what we are left with is 4 milliamps, because if it needs to signal 4 milliamps, then the whole sensor, it needs to be taking maximum 4 milliamps from the loop, and 4 milliamps is all that is left for powering all the device. The back end, the microcontrollers, the front end. So you can see some power budgeting here. And what is left for the instrument is, and we lose some power on the barriers and on the cable, because the cable, if it's long and has some resistance, you have some voltage drop of the cable. There is an intrinsic safe barrier, which there is no way around that having a resistor in series. So again, you have some voltage drop there. So what is left for the instrument itself is something in order of 40 milliwatts. You can argue it's 38 or 45, but in order of this. And for the measurement itself would be around 25 milliwatts. So 25 milliwatts is all that is left for the sensor, analog front end, A to D converters, microcontroller running the algorithm to calculate from the voltage from the sensor, pressure, or whatever is being measured. If we compare now to the 10BASE-T1L APL device, and I'm referring to APL port specification class A, which is a half a watt power. The system is delivering similar power, about half a watt of power going to the communication line. And the specification says that you need to account for minimum 9 volts on the instrument, about 55 milliamps that can be taken by the instrument. We are going to use much more power on the protection. We use more power for the communication itself, but we still, and it's our focus to make low power communication. You will need a little bit more power on the microcontroller just to run protocol, and it depends on what protocol you are running. It will be different if you run full blast Profinet and different if you run something simpler, but roughly the power budget there. So from the 500 milliwatts that is delivered by the port now, we end up about 250 milliwatts left from the sensor itself. So it's about 10 times more than we had in the 420 milliamps, which means we can build more sophisticated sensors, and we can maybe transfer more sensors that previously on the 420 milliamp loops would need external power supply, couldn't live from the 420 milliamp loop. So we can maybe transfer more sensors because we have more power available. We can transfer more sensors to the two-line single pair communication. So that's power aspect of the design. Explosive safety. Explosive safety is being built, intrinsic safety instruments for 420 milliamp loop are being built for a long time. There is a barrier that limits how much power, how much current, how much voltage can you get to the line. And then the instruments have to be able to safely operate under that power budget. And safely operate is the philosophy of the intrinsic safety, that you have to consider anything can fail. You can't count that one diode will work, and that's why you can see 3 diodes in series in the signal path, if you think about that in any polarity. Any component can fail, so if the component is critical for limiting the power that can be dissipated inside the instrument, or if the component is guaranteeing you don't have much than expected voltage on capacitor, all these things have to be either very simple, my apologies, has to be either very simple components, or they have to be doubled. So there is clumping, and there are well-known techniques in the industry. You have maximum voltage 30 volts from here. You may be clumping voltage lower on the instrument side, because if you clamp the voltage lower, you can afford more capacitance. And just again, the philosophy here is, if you accidentally short this capacitance by damaging the instruments and you short it, it must not spark. Because if it sparks and there is hydrogen outside, it will just blow up the factory. And similar temperatures, if any of the device fails, completely fails, and starts heat up and dissipate the power, under the maximum power dissipation for each section of the device must not exceed temperature that could cause ignition of the environment around. So for 4 to 20 milliamp device, the maximum power that the whole instrument can dissipate is about 0.75 watts. So it has to be designed in a way that that power dissipation does not cause temperature that could cause some damage. Now, if we compare now with the APL device, the philosophy and the techniques around are very similar, if not same. The APL specifications specify how much power can deliver the 10BASE-T1L spur port. So the intrinsic safe barrier now is effectively built inside the switch. And it says how much voltage can be expected, how much current can be expected to go to the device. There's some more protection needed for the power coupling. And you can see a large number of diodes there. There has to be 2 columns of diodes in parallel just in case one of the diode fails. The other still needs to be able to clamp. And when mentioning these diodes, the 10BASE-T1L amplitude to explosive environment is limited to 1 volt. The standard recognizes 2 amplitudes, 2.4 volt, 1 volt. So 1 volt is used for this intrinsic safe instrument, not because the 1 volt carries less energy, but because you can effectively clamp the components inside the device. So that 1 volt amplitude, if you think about diode, it cannot forward bias by the signal itself. So you need at least two diodes, two diode voltage drops that don't open in 1 volt. And if you go 2.4 volts, there will be much many diodes. And then inside the instrument, the techniques are the same as in 4 to 20 milliamp loop. So that compares 1 to 1. So the only thing to watch if you design 10 base T1L device for intrinsic safety, the power that it needs to be able to dissipate is now about 5 watts. And that comes from the Fisker principle, from the APL specification, but it's not completely new because this technique and this power level is already used in some foundation field bus or Profibus PA devices today. So that's explosive safety. Again, design is not much more complicated than existing 4 to 20 milliamp loops. And then functional safety. If you design functional safety instrument, you have to be sure that what you think you measure is actually what you measure. So the A to D converter, if the A to D converter failed, you need to know it and you need to detect it and report to the rest of the system. So you would see techniques like having redundant A to D converter, redundancy in the front end of the measuring. But what's more interesting is the 4 to 20 milliamp loop itself. Again, remember, it's an analog signal. 4 milliamps is 0%, 20 milliamps, 100%, and anything in between represents a value that is being measured on this by the sensor. So if you want to make sure that the 4 to 20 milliamp loop represents what sensor is measuring, you need to make sure that if the microcontroller says, I don't know, 12 milliamps, you have to watch that it is really 12 milliamps, which means some additional components, additional techniques in the signaling, in the 4 to 20 milliamp output loop driver itself. So you would see typically another resistor, ADC, looped back to the microcontroller, and similarly on the input side, on the analog input side, on the controller, you would see some, again, redundancies there. You wouldn't rely on one resistor. You would have two resistors, two A to D converters, again, to make sure that what sensor measures, that information gets all the way down there. And if it doesn't, if there is any fault detected at any stage, you have to declare that the sensor can't measure. So if you can imagine, you are watching a level in some tank, and the tank has some dangerous chemical, you want to make sure that it doesn't overflow. So you have to make sure that what you measure as a level is actually what the level is, because if you overflow, you can cause some damage, kill some people, and so on. So that's functional safety. And again, 4 to 20 milliamp loop, you have to design to the functional safety standard, and it's a parent standard for functional safety. All the signal chain, including your communication, needs to be designed to that standard. Now, if you compare with the APL instrument, the same techniques, the same functional safety, the same redundancy applies for the analog front end connected to the sensor. But once you get to digital, it's relatively easy. It's a black channel. You either do get communication or you don't. And you can apply, of course, you apply some safety protocol. If you run Profinet, you will apply Profinet safety there. You can easily detect that the packet that is sent by this microcontroller is correctly received on the other side. You do CRCs and so on, and you know that you have to get new packet. You can number the packets, so you know that the next packet is not the same as the previous one. There are techniques around that, but these techniques are digital and do not apply for the communication, for the APL communication itself. So there's functional safety. Now security. If you look at the plant, and if you look at on the left-hand side on the plant wire 4 to 20 milliamps, and if you look, how can you cyber attack that plant? You can come from the cloud, from internet. You know, there may be many people interested in taking your plant down, but it's kind of on the IT level. So you would have, of course, you would have some firewalls and security built up there. But then if you look at the perimeter of plant, of course, you need to sort out security in your plant. If somebody gets inside and can pull a wire, then you can't do much about that on the electronic side. So you have to have a security of your plant sorted. But then if you go down to the field, if you have some device, if you can attack one device, and I put one device deliberately on the edge, so it could be your, I don't know, intake of material to your plant, you may have some sensors there, so somebody unauthorized can access that sensor. Okay, he can access that sensor, he can damage it or fake it, but it's only one sensor of many that are inside the plant. So yes, you can take one sensor down, one 4 to 20 milliamp loop is lying or doing something strange, but as a control system is still doing what it's supposed to do. If we look now at the 10BASE-T1L and we say seamless connectivity, collecting data from the edge to the cloud, that means it's a network. And once you access any node of that network, you can potentially get through the network and you can attack all plants, all of your plant, if you are able to attack and fake one of the sensors. And that's why, if we talk about 4 to 20 milliamps, we usually don't talk about security at 4 to 20 milliamps. I have not seen anybody in the industry, building a security 4 to 20 milliamp loop transmitter. But if you go to the 10BASE-T1L, you have to make sure that the device that is connected to the network is what the device is supposed to be. You need to make sure that it's running the correct firmware in your microcontroller, that somebody doesn't put something different there. And we discussed the microcontroller. If the microcontroller is able to run a Profinet stack, it can equally run some rogue kind of firmware there. So you need to make sure that the firmware is what's supposed to be, so you need to apply some secure boot. You need to apply authentication on both directions. So from this side, you need to make sure that you talk to the device that you are supposed to talk, and equally, if the device is getting a firmware update, it needs to make sure that the firmware update is coming from an authorized source, and you typically use encryption and so on. So there is a security IEC standard that applies to the industry, and in the APL instrument, you need to apply security. And there are chips for providing these functions in the instruments. So that's the security. And that's just a quick summary of what we talk about. So comparing 4 to 20 milliamp and 10BASE-T1L from the edge device point of view, from design of the edge device of the field instrument. So quick comparison. So 10BASE-T1L, you can get all data that you want and are available upstream, downstream. You can get seamless connectivity from IP addressable end device up to as high as you allow your plant. To the cloud, you can collect lots of data, use them for optimization, monitoring, and so on. You actually can get much more power for the instrument, for the measurement itself, for the APL device, about 10 times the power than the 4 to 20 milliamp loop was providing. Intrinsic safety, there are known techniques. You have to deal with a little bit more power that you need to be able to burn in your instruments. Again, there are techniques how to stage the power limiting. And again, we will have solutions for that in chips. And connection is actually, from the functional safety point of view, the connection is easier. The channel itself is black channel. You don't care. You either do get data or not. Whereas 4 to 20 milliamp, any value in between could be wrong. And then security is something critical that you need to implement on the end device. And that's the price that you pay for seamless connectivity up to the cloud. And that's for me. If you have any questions, feel free.